explore what is the effect of the CTF and the different ways to correct for it. So let us take our favorite PDB. So this is just a relatively small PDB, and the pixel size here it is 0.75 angstroms. So we create a gallery of these images. So let us see if I can, yeah. So we have projections of these structures, so we can change here the magnification. So with that we see that we have almost all orientations here, and if you're interested in how to generate those images, you have to say here what is the rotational angle, minimum 0 to 316 steps of 5 degrees, and the same for the tilt that goes from 0 to 180. Okay, so now we will apply the focus to each one, to this gallery. We will have three different scenarios. So the first one, we will have low defocus. So low defocus, this defocus is in angstroms, and it is under focus, so we have between 0.2 to 0.5 microns in the focus. So the result here looks like this. So you can compare the differences between these kind of images. So let us open the first one. So the first one here, and now the first one on the CTF. So this is the original one. This is after a low defocus, and this defocus was between 0.2 0.5 microns. So let us put them there. Now we have a different set of particles. So now we have much more defocus. Let us check the parameters. So here the parameters are between 0.5 to 2 microns. This is the typical defocus. So typical defocus here. So this is how low defocus. This is low defocus, typical defocus, and then let us go for high defocus. High defocus is between 4 to 5 microns. So again, we open that image, and now we will comment on all these details. Okay, so here we have all the different images, and let's see what is the effect of the CTF. So for a clean projection, the image is concentrated where the projection, these line integrals are, and yeah, so we have zero outside, or almost zero outside, and inside we have the values of the sum of the Coulomb potential of the object along the ray path. And when you have a CTF, or when you defocus these structures, this information is convolved with the point spread function of the microscope, and these oscillations here are caused by this point spread function. So the point spread function looks like a kind of sinc function, and so it is sinusoidal, and it decays with space. So and the decay is larger, or it reaches longer distances as the defocus increases. So for low defocus we have a short range. For typical defocus we have a longer range, and for very high defocus you have a very long range, and very highly focused also means in Fourier space you can think of this as a low pass filter, again oscillatory low pass filter. So you lose the high frequencies, so the more you defocus, the more frequencies you lose, and these patterns here in the borders, they are caused by the application of the CTF on the Fourier space, because the Fourier space assumes that the images are periodic. So our image here is repeated everywhere in a kind of crystal, and then what we are seeing here is the convolution of the nearby cell convolved with the PSF. And then part of that information comes into our own cell that we are considering. This is an artifact of the application of the PSF. In Fourier space, we can fix this by padding. So if we increase the size of this image by padding by any number of pixels, these nearby cells get farther and farther, and if you take them farther enough, then these ripples coming from the nearby cells will not occur. So this is the first thing to take into account. The padding must be sufficient so that we don't have nearby cells interfering. And the padding also has an implication in how fine we are sampling in Fourier space. Okay, so the final image I would like to show is this one, where we correct, or there are a couple of them, where we correct for the PSF in two ways. First way is by phase flipping, so we can see how the phase flipping changes this image, and what we see here is and let me open the last one. This is the binary correction. So binary correction almost recover the original one. Okay, so we have the different versions of our image. This is the phase flipped, so this corresponds to this one, and this is the binary correction. Let's put it there. So these are the different foci, and this is the phase flipped. So because of the oscillations means that some frequencies when the CTF, where the CTF is positive, that means that the protein is projected in white over a darker background. So this is what we see here. The main bulk of the protein is white, but some frequencies are multiplied by negative CTF. So that means that the protein information for those frequencies is projected as black over a white background. So this happens here. So the phase flip only changes the sign of the CTF, so that the CTF is all the time positive. So we see that there is not such a big change. And normally with noisy images, with the protein embedded in eyes, it is very difficult to see all these details, so that is why we are doing it with simulated data. And then the binary filter. The binary filter corrects for the phase flip and the amplitude. So the decay of the CTF is so the CTF is going down, is falling in frequency. So we divide somehow by the CTF to recover the original amplitude, and these two images are much more similar. So they are not exactly the same, but certainly much more similar. Okay, so let us close all this, and now let's go to some particular thing, that is binary binary correction has a constant that is related to the signal to noise ratio, and you have to estimate. There are algorithms that try to estimate, but depending on which is this constant, this correction can be pretty good or can be pretty bad. So just pay attention to that. And what happens if we reconstruct without taking into account the CTF? So if we don't correct for the CTF, we use the raw images to reconstruct. This is what we get, which is not very pleasant. We see oscillations around this dark area around the particle is caused by a miscorrection of the CTF. So this is one reconstruction. If you reconstruct using the CTF, so taking into account explicitly the CTF, now you can recover exactly the original structure. So you can compare similar slices. So this slice is this slice, and you see that the appearance is pretty different. And also, if you use perfectly the if you correct perfectly for the CTF, you don't have any ripples around. So very often we see these dark areas in 3D reconstructions around the structure, and part of it is caused by a miscorrection of the CTF. Okay, so now let's do something that we have already seen here is that the information from the particle is delocalized and it is spread over the nearby regions. And how much, it depends on what is the defocus. So for instance, if you have a low defocus, it will be more centered on the particle, but if you have a larger defocus, then this information will be spread around. And these are the typical defocus values that we use in electron microscopy in single particles. That is somewhere between 0.5 and 2 microns or 2.5 microns at most. So we have from relatively little spreading of the information to a much larger spreading. So here we have a mixture of everything, and if you correct exactly with the correct defocus that here we know because it is simulated data, then you can recover exactly the structure as we saw here. So what happens if we now crop the particles? So these particles are 200 times 200, the pixel size 0.75. We don't change the pixel size, but we change the box size. So if we now change the box size, part of the information you see that was spread around is cropped. So that means that we don't no longer have that information. So does it affect a lot the 3D reconstruction? So we can make a reconstruction, and then I put it back to the size of 200 just to make it everything comparable. So we see that especially when we compare to this one, so let us do it with the perfect one. So in the perfect one, let's go to some slide. So this is a slice 116. We can compare to this one. So they are pretty similar, but we see that there is a kind of, this is a little bit more blurry. There is a kind of haze on top. And the reason is this loss of information that because the information from the particle has been spread around, but we have cropped the projections, then we have this kind of blurring around. And again, this blurring is something that we often see in many reconstructions. And then the same happens if we keep the original size, but we apply a tight mask. So this is a mask on the images that should not be confused with a mask on the 3D reconstruction. That is different. Okay, so here we will have the same effect, only that we have more space around, but this space around is 0. So we have again lost this information, and we have kind of the same result, where we have the right structure but with a little bit of haze on top. Okay, so the final thing is okay, so we have reconstructed with Wiener, and now we apply a Fourier reconstruction, and a Fourier reconstruction here now it looks good. Okay, so it looks like the correct structure without this loss of information at high frequencies. And just to be clear, to make all these corrections, and the same happens when you are reconstructing. So these corrections need that, so a Wiener filter, rely on reconstruct, or any reconstruction that takes explicitly into account the Fourier transform, or not the Fourier transform, the CTF, or the phase flip. They all need the information around. So if these images have lost this the information around, and here we see that some of them are already a little bit too tight, because we see the nearby copies, so that means that also this copy wanted to spread a little bit more. So the information can be quite spread. Actually, we can measure what is the size of this. So we can, for instance, make this. We can so we can measure in pixels how far this information is going. So this information is going from the particle. It is going almost 60 pixels away, and now we measure from here to the end of the ripples, so it is another 60, so it is like 120 pixels away. 120, the pixel size here is 0.75, so it is 3/4 of 120, that is around 80 angstroms. So you should have your particle and around 80 angstroms around to have to fully contain the information from a given particle. If you don't have these 80 pixels around, 80 angstroms around in each direction, then you are losing a bit of your information, and then your 3D reconstruction will not be perfect. But then if you go 80 angstroms around, you have the risk of having nearby particles, and then you also have on top of your particle, you have the information from the nearby particle. So this is a bit of a compromise between having all the details from a given particle and not mixing information from nearby particles. So this would be all for the understanding of the CTF. See you in the next project.